So now we're going to get back to the pizza recipe, where 1 crust, 5 ounces of tomato sauce, and 2 cups of cheese yields 1 pizza. So assuming in your fridge you randomly have 4 crusts, 10 cups of cheese, and 15 ounces of tomato sauce, we want to figure out how many pizzas can you possibly make. Now, you might be able to do this in your head and figure out, what's the maximum amount of pizzas you can make, but we're going to use our calculations and stoichiometric ratios to help us figure that out. So I'm wanting to calculate how many pizzas I could make. So let's think about for crusts. If I have 4 crusts in my fridge and I want to make a pizza, well, I know from my recipe, i.e. chemical reaction, 1 crust gives me 1 pizza. So just thinking about with crusts, I could make 4 pizzas. With cheese, I have 10 cups of cheese in my fridge. So I can look at my recipe and notice that I have 2 cups of cheese for every 1 pizza. So I could make potentially up to 5 pizzas with my cheese. And then with my tomato sauce, I have 15 ounces of tomato sauce. And from my recipe, I use 5 ounces of tomato sauce for every 1 pizza. So I can make, with that amount of tomato sauce, 3 pizzas. So 4 pizzas with my crust, 5 pizzas with my cheese, and 3 pizzas with my tomato sauce. That means that I really can only make 3 total pizzas because my tomato sauce is going to limit me. So even though I can make 4 pizzas with crust, 5 pizzas with cheese, the 3 pizzas from my tomato sauce means that that's the maximum I can make. So therefore, we say the tomato sauce limits the amount of pizzas I can make. The tomato sauce is the limiting reactant because it is one of the ingredients that is going to limit how much of our product we can make or how much of our pizza. So our amount of pizzas that we can possibly make, it depends on that ingredient. That maximum amount of product is called the theoretical yield. So the theoretical yield is connected to the limiting reactant. Limiting reactant is the reactant that we can make. Theoretical yield is the maximum amount of product, and they are tied. So when you find the theoretical yield, you learn who is the limiting reactant. If we go back to the pizza analogy, assume that when we're making our pizzas, one of our pizzas is burnt, and so we can only eat 2 of those 3 pizzas. So the actual amount of product that is made is called the actual yield, and that would have to be given to you. Well, one, you could do it if you did an experiment. That would be what you get in the lab, or it is given to you. So the actual yield is all about efficiency. How efficient is your reaction? Did it go to completion? 100%? Unlikely. Or did you get a large amount or a small amount? So ideally in cooking, we get a decent amount of efficiency, but in chemical reactions, a lot of times they don't go all the way to completion. So in this case, we would want to calculate our percent yield, and that would be to take our actual yield that I'm just going to put AY, actual yield that we got in lab divided by your theoretical yield that we calculated times by 100, and that would give us our percent yield. So in this case, we actually made 2 pizzas. We could have made up to 3 pizzas, and so I times by 100, and I get 67% yield. So kind of a bummer, but this is another equation you're going to need to know. So just to summarize, our limiting reactant is the thing that limits the reaction because it gets used up first, and so no more product can be made. The other reactant is an excess, and so that's where we're going to have leftover. Theoretical yield is what our limiting reactant predicts we can make. The actual yield is what we do get from experiment, and percent yield is actual yield divided by theoretical yield times by 100%. Gives our percent yield. So let's bring it back to chemistry. If I have ammonia being synthesized by this reaction, if I start with 86.3 grams of nitrogen monoxide and 25.6 grams of hydrogen, what's the theoretical yield of ammonia in grams? So I'm going to start by going with my 86.3 grams of nitrogen monoxide and 25.6 grams of hydrogen. Notice these are both reactants. If they ever give you a product, numbers for a product, don't ever start there. You don't need to. It's a product. It can't be a limiting reactant. Hint, hint, it's a reactant. So here are my two reactants. I'm going to start there. And I'm going to go to a product. Now, to find my limiting reactant, I can go to any product. But in the case here, they want us to find the theoretical yield of ammonia. So I'm going to go to ammonia using stoichiometry. So let's get to moles. I'm going to take nitrogen monoxide, 30.01 grams per mole. And then I'm going to go to moles of ammonia. So there's 2 moles of nitrogen monoxide for every 2 moles of ammonia. And, whoa, we can calculate that answer. So we get 2.8757 moles of ammonia. You can go all the way to grams of product if you like, or you can stop at the moles before doing your last calculation. So now I'm going to go hydrogen. I have 2.02 grams per mole of hydrogen. Using moles of hydrogen to moles of ammonia. 2 in front of ammonia, 5 in front of hydrogen. And we get 5.0693 moles of ammonia. So it looks like I look for the smallest amount. That's going to be the thing that limited my reactant. So here's my lowest amount. So nitrogen monoxide is my limiting reactant. Hydrogen is in excess. And so then I can now take this and go to grams. So I have 17.03 grams per mole of ammonia. So that gives me my mass of 49.0 grams of ammonia. Okay, so now here's another way that I can synthesize ammonia with hydrogen and nitrogen. So what's the theoretical yield of ammonia in kilograms that we can synthesize? So if I have 5.22 kilograms of hydrogen and 31.5 kilograms of nitrogen. So once again, we need to get to moles. So we have 1 kilogram per 1,000 grams. And then we go to moles. So I will have 2.02 grams per mole of hydrogen, and then I can use mole of hydrogen to mole of ammonia. And I have 2 ammonia and 3 hydrogen. So I'm going to go straight to the end. So now I can go moles to grams. I use molar mass of ammonia, and then in 2 kilograms. 1,000 grams in 1 kilogram. For nitrogen, we'll do the same thing. 1,000 grams in a kilogram. And I'll use my molar mass, 28.02 grams per mole. And then I can use my stoichiometric ratio. So moles of nitrogen, moles of ammonia. 1 in front of nitrogen, 2 in front of ammonia, and the rest of it will be the same. So after I calculate all of that out, I get 29.603 kilograms of ammonia from hydrogen, and I get 38.290 kilograms of ammonia from nitrogen. So it looks like my theoretical yield is that lowest amount, and my limiting reactant was hydrogen. Okay, in this example, we have titanium oxide and carbon reacting to form titanium and carbon monoxide. I have 28.6 kilograms of carbon reacting with 88.2 kilograms of titanium oxide. And then I produce 42.8 kilograms of titanium. Find the limiting reactant, theoretical yield, and percent yield. So notice, they give me a product. Do not start with the product. You want to start with your reactants. So we have 28.6 kilograms of carbon, 88.2 kilograms of titanium 4 oxide, and let's go from there. So I want to get into titanium since that is the product that they end up measuring. So let's go kilograms. 1 kilogram is 1,000 grams. I have 12.01 grams per mole of carbon. Then I can use stoichiometry, moles of carbon to moles of titanium. So I have a 1 mole of titanium for 2 moles of carbon. I'm going to stop here, and this gives me 1.1907 times 10 to the third moles of titanium. Using titanium 4 oxide, I'll use the same beginning, and then I can use my molar mass of titanium oxide is 79.87 grams per mole. Key thing, Ti and Tl, different elements. Make sure that you're paying attention because titanium oxide is much smaller than tellurium. And then I can use mass of stoichiometric ratio, moles of titanium 4 oxide and moles of titanium. This is a 1-to-1 ratio. And I get 1.1043 times 10 to the third moles of titanium. So this one's really close, but this one ends up being the limiting reactant, or the theoretical yield here. So our limiting reactant is titanium 4 oxide. Theoretical yield is that many moles, so let's just take one more step further and get that mass. So I use the molar mass of titanium, 47.87 grams per mole, and then we gotta go all the way to kilograms. So 1,000 grams in 1 kilogram gives me a mass of 52.9 kilograms of titanium. So in their experiment, they produced 42.8 kilograms. So if I want to find percent yield, I'm going to do actual yield from the experiment over theoretical yield times 100. And that will, so I'll get 42.8 kilograms divided by 52.9 kilograms times 100. My theoretical, or my percent yield is 80.9%. So pretty good. In this example, we have iron 3 oxide and carbon monoxide reacting to form iron and carbon dioxide. If we have 167 grams of iron oxide and 85.8 grams of carbon monoxide, here are my reactants, they produce 72.3 grams of iron, so that's from my experiment. Determining the limiting reactant, theoretical yield, and percent yield. So we're going to end up going into iron because that's what they did experimentally. So let's use the molar masses of iron oxide and carbon monoxide. So iron oxide has a molar mass of 159.69 grams per mole. Now I can go from moles of iron 3 oxide to moles of iron using the stoichiometry. So 1 iron oxide, 2 moles of iron. And that gives me 2.091 moles of iron. Here for carbon monoxide, I have 28.01 moles. Whoops, I lied, grams per mole. And now I can use moles of carbon monoxide to moles of iron. 2 moles of iron, 3 moles of carbon monoxide, and that gives me 2.042 moles of iron. So my lowest amount is here. So carbon monoxide is my limiting reactant. One more step to get the mass. So I'm going to use mass of iron oxide, 55.85 grams per mole. And I should produce 114.05 grams of iron. So percent yield is going to be actual yield over theoretical yield times 100. In an experiment, we produced 72.3 grams of iron over the 114.05 grams that theoretically could have been produced times 100, and that gives me 63.4%. Also, not bad. If we go back to the titanium 4 oxide example, we still have the same amounts. Remember that our limiting reactant was a titanium oxide. We want to find the mass of excess reactant, so carbon, that is after the reaction is complete. So you might think, I'm going to start with carbon, but no. What you want to do in these cases is you want to start with your limiting reactant. So my limiting reactant is titanium oxide, 88.2 kilograms of titanium oxide. It's going to run out first, so we want to start with it. We need to find out how many moles of it are going to react. So we're going to get into kilograms, from kilograms to grams, 1,000 grams. And now we use the molar mass of titanium oxide, so again, 79.087. Notice this should be very similar to the beginning of our last one, but here's the key pivotal moment. We're going to go now from moles of titanium oxide to moles of our excess, which is carbon. This is where we are going to find out basically how much carbon gets used. So now let's go back to kilograms. So I have 1 mole of carbon has 12.01 grams, and we get to kilograms, 1,000 grams in a kilogram. Great, so the amount of carbon that ends up reacting is 26.525 kilograms of carbon. So that's how much get used up. Now notice there was 28. So to find out how much is left, I'm going to take the amount I started with, 28.6 kilograms, subtract how much got used based off my limiting reactant, find out how much is left, which in this case is 2.1 kilograms remain. If we go back to the iron oxide example, then we're going to, again, start with the limiting reactant, which in this case is carbon monoxide. So let's start with 85.8 grams of carbon monoxide. Now I'm going to go to how much iron oxide gets used. So I have 28.01 grams per mole. Now moles, key point, carbon monoxide to moles of iron 3 oxide. Whoops. So we have 1 mole of iron oxide for 3 moles of carbon monoxide, and then we'll go to the mass of iron oxide. That's 159.69 grams per mole. So the amount of iron oxide that gets used up is 163.05 grams. So to find out how much is left, I'm going to take the amount I started with, 167 grams minus the 163.05, and that means I have 4 grams of iron oxide left over. Okay, so we built all of that math up so that we can eventually talk about actual chemical reactions. And you've been doing them already, but the first one we're going to start with is our favorite, combustion. So a combustion reaction happens when we react a substance with oxygen to form one or more oxygen-containing compounds. So oftentimes this is going to be water and heat. And generally, if carbon's involved, you're going to have carbon dioxide. So here is the combustion of methane. Methane is CH4, it's a gas, and it's going to react with oxygen, gas. Now, notice there's carbon and hydrogen. So both of them are going to mix with oxygen. So we'll form CO2, gas, and hydrogen and oxygen will give us water. Generally, I don't know if you've noticed a huge puddle of water after you've lit a fire, but generally the water is so hot that it turns into vapor. And then we also get heat out. Now we need to balance it. My carbons are balanced. My hydrogens, I'm going to put 2 here to balance out those 4. Now my oxygens, I have 1, 2, 3, 4 here. So then I need 2 out here. A nice simple one, but as you saw earlier, they're not so simple. Okay, so I have methyl alcohol, methanol here. Now, when I write it to balance, I usually write CH4O to put these together so I don't forget a hydrogen, which has happened. So I'll CH4O, and then I'll rewrite it later to make sure that I have it written the right way. Technically it doesn't matter, but this is really more of how it's structured. It's in the liquid phase. It's reacting with oxygen, gas, to produce CO2 and water. You don't have to write heat more than just that time. Just know it is exothermic, which you should be familiar with. So carbon, hydrogen, oxygen. Product reactants I have 1 and 1. Hydrogen I have 4 and 2. And oxygen I have 2 here, 1 here, 3. And then over here I have 3. Looks good, but actually those oxygens in every single molecule tends to be a pain. So let's balance. So first I'm going to balance the hydrogen. I have 2 here, making that 4. And then my oxygen becomes 4. Now notice with oxygen, I have an odd and an even. So just by default, when that happens, I'm going to have to multiply it by 2 since they show up in multiple places. So I'm going to do a 2 here, 2 here, I guess, and then a 2 here, and a 4 over here. You have to do that when you have the odd and even because it doesn't work out if you don't. So now I have 1, 2, 3, 4 over here. I have 2 carbons on each side, and my hydrogens are balanced with 8. So let's figure out my oxygen situation. I have 1, 2, 3, 4, 5, 6, 7, 8. So 8 oxygens over here. And I have 1, 2 here. So in order to not mess anything up, I need to make this a 3 to make that a total of 6 oxygens. So it will balance. Here's another one. I have this interesting compound that has, instead of an alcohol, it has a sulfur. It's a liquid. It reacts with oxygen for the combustion. Now it's going to form molecules that have carbon, hydrogen, and now sulfur. So we have carbon dioxide, gas. I also now get sulfur dioxide, gas, and water. So we're going to need to balance now an extra element. Carbon, hydrogen, sulfur, and this is really a 6, right? H6, we'll put there, and oxygen. So I have 2 carbons on that side, 1 over here. I have 6 hydrogens, and then 2 over here. Sulfur gives me 1 and 1, and oxygen. I don't even want to deal with oxygen until the end. And actually, you know what? I'm not going to deal with it until I balance everything else. So let's balance out our carbon and hydrogen. So I'm going to make this 2 and this 3 right off the bat. And that changes my carbon to 2, hydrogen to 6. Okay, so now I'm going to add up. Now that everything else is balanced, I'm going to start to deal with the oxygen. So I have 2 here, and then 1, 2, 3, 4, 5, 6, 7. So an odd and an even. We know what to do. We're going to have to multiply everything. 2, we'll have 4 and 6. Okay, so 4, 2, and 6. So now I can get rid of all of my numbers and basically just start over. Okay, so I have 4 carbons here, 4 carbons there. I have 12 hydrogens there, 12 hydrogens there, 2 sulfurs, 2 sulfurs. Now 2 oxygens, and I have 1, 2, 3, 4, nope, 8 here, plus 4, 8 plus 4 plus 6 gives me a total of 18. So I have 18 oxygens. So then I can multiply this by 9 to give me that last, the 18 over here. Okay, the next type of reaction is alkali metal. Remember, they are group 1 elements. They have an NS1 electron configuration, which means that they like to form a +1 cation to be like their closest noble gas. And so these reactions with nonmetals are pretty vigorous because the alkali metal wants to give that electron away so bad, and those nonmetals really like to take them. So common reactions with alkali metal being M and halogens being X would be metal, solid, any of those first rows, plus remember those alkali or the halogens show up as diatomics, and they could be liquid, gas, or solid, doesn't really matter because they all have a different state. React to form. Now, metals, the alkali metals like to be +1, and halogens like to be -1. So they'll just form that, and it could be solid, or generally it's going to be solid. Anyway, so then I'm going to balance that. I have 2 halogens, so I need 2 over here. 2 metals now, make 2 metals here. So a common example of this is forming salt, where I have sodium plus chlorine gas reacts to form sodium chloride, our most delicious salt. And that is a solid, as we know. Alkali metals also react with water to form alkali metal ion and hydroxide ion and hydrogen gas. So what we get is metal solid reacting with water, liquid, gives us metal hydroxide. So metal is a +1, hydroxide is a -1. Both of these will be aqueous. And hydrogen gas. So in order to get that, we're going to need 2 hydroxide and metals to react. So we get 1 hydrogen gas molecule from these 2 compounds. This is very exothermic and can be explosive. We saw this in class, a video of some of these, and they're pretty cool, but pretty vigorously reactive. The last reaction type is the halogens. So group 7 elements, they have a NS2 and P5 electron configuration. So they're really close to being like a noble gas if they just gain 1 electron and form the -1 anion. So they are the most reactive nonmetal elements. They, like we saw earlier, they can react with technically any metal, not just alkali metals, and so to form metal halides. So that how that happens is I get a metal plus a halogen produces some metal halide, and that could be a variety of charges. We'll call those N. So in order to get this reaction to balance, we'll need 2 metals and then N amount of halogens. So an example of this is iron metal plus chlorine. Gas produces iron 3 chloride. That is a solid. So then we would, because we have 3 chlorines, I'm going to need 3 out here. I'll need 2 here. for those to balance out. They tend to react with hydrogen to form hydrogen halides, so we get hydrogen gas plus my halogen with any phase that it might have produces hydrogen halides, and those are gases generally, and so we'll produce 2 of those. And then the very last one is interhalogen reactions. So halogens reacting with each other. So we'll call one halogen X, another halogen Y, and they'll produce those interhalogen compounds. So each of those, and we get 2 compounds out total. So let's practice. I want to know the reaction between potassium metal and bromine gas. So potassium is an alkali metal. Looks like that in its natural state, plus bromine. Bromine is actually generally not a gas, it's usually a liquid, but whatever. It must be heated. So we're going to form potassium is a +1, bromide is a -1, and then we are going to have, this is a salt, so that should be theoretically solid. So I'm going to need, I have 2 bromines, so I'm going to have to put a 2 out there and then a 2 out there. The next one we have rubidium and water. So rubidium, Rb, solid plus water gives us, now rubidium is an alkali metal, so it's going to produce rubidium, oops, Rb, not Ru, sorry, +1, aqueous, plus hydroxide, plus hydrogen gas. And then we'll need 2 of each of those, and 2 of these to give us that 1 hydrogen. And you wouldn't be wrong if you wanted to do like 2 RBOHs aqueous, because when we write those, they're equivalently they could be broken up or together. Because they're aqueous, it's kind of implied. C, we have gaseous chlorine plus solid iodine. That should give us that interhalogen, so whoops, not X. We'll now have Cl and I, and we'll have 2 of those. And I'd have to tell you the phase, because honestly I don't even know what it is. We can put gas, but I'm not really sure. Okay, the next one is aluminum and chlorine. Oops. Aluminum metal, that's a solid, plus chlorine gas. Gives aluminum is +3, and chlorine is -1, so I'll need 3 chlorines. So for that, I have 3 chlorines out here, 2 here, so I'm going to put a 3 here and a 2 here to make those a total of 6, and then I'll need 2 aluminums out front. And if you want to follow the recommendation of the last slide, or you can just balance it and use ionic charges. Next one, lithium metal and water. Lithium plus water. This is going to do something similar as above. It gives us lithium hydroxide, aqueous, plus hydrogen gas. I'm going to need 2 of everything except for the hydrogen. And then last one, F, hydrogen gas and bromine liquid. Gives that hydrogen halide, hydrogen bromide, say gas, and I'll need 2 of these. And that should be Br2. Okay, that is it. So we'll continue on with chapter 8, learning way more types of reactions.